Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is another video on my feature on my daily math problems, which I post every few days on the Facebook group Classical Mathematics. This is one I posted a few days ago involving pretty important mathematical constant called the rabbit constant. And anyway, let's begin. So here's the statement of the problem. So first I define the rabbit constant. The rabbit constant, which is usually denoted by the letter capital R, is the mathematical constant defined by the following recursive procedure. So for step 1, we let R0 equal 0. And then for step 2, we do an iterative process. We say for n greater than 0, we let greater than equal 0, actually, we let Rn sub n plus 1 be the number obtained from R sub n by replacing each 0 in its binary representation after the decimal point with a 1, and each 1 with the string 1, 0, leaving the final 0 intact. So, and then finally for step 3, we let R be the limit of R sub n as it approaches infinity. So for part A, I'm asking for the exact value of R sub 10. And for part B, I'm asking for the first 9 terms of the continued fraction of R sub 10. And I'm also asking if you can find a pattern to those continued fraction coefficients. And I think this is a really interesting problem, and I thought I'd just share with you. This is the Wolfram Math World page on the rabbit constant. Wolfram Math World is a really excellent online and math encyclopedia, by the way. If you haven't seen it, I recommend it. And I actually contributed to this article here. If you can see on the bottom of the slide, my name is here, D. Tear. Actually, what I did was, let me just, I'll talk about this at the end, because what I did was kind of minor compared to the definition. But, here's the approximate decimal value of R. They give it to 20 decimal places. I also did on the cover slide. You can compute it to an arbitrary number of decimal places, but anyway, um, so and I guess I should mention. So right after they show the decimal expansion, they show what its continued fraction looks like, and it has a really fascinating continued fraction. The first coefficient is 0. All that's saying is that R is less than 1. It's a positive number between 0 and 1. And then every following continued fraction coefficient is 2 to the power f sub k, where f these are Fibonacci numbers. So the one after the 0 is 2 to the f sub 0. Then you have 2 to the f sub 1, 2 to the f sub 2, 2 to the f sub 3, where f sub k is the kth Fibonacci number. Pretty amazing that it has that form. Because that didn't go into my definition. And actually, I don't think they even give the definition the way I did on this page, which I'm a little surprised by. But anyway, then the thing on the bottom, this was my contribution, actually calculated the irrationality measure of the rabbit constant. I'm not going to go into what that is. It turns out that almost all irrational numbers have an irrationality measure of 2. And that just means that they're difficult to approximate by a series of rational numbers. I think they really should call this thing the rationality measure, because the bigger the irrationality measure is, the easier it is to approximate these numbers by rational numbers. And it turns out that the rabbit constant is easier to approximate by rational numbers than most irrational numbers are. And the value of this irrationality measure is approximately 2.618. So it's bigger than 2. 2 is normal. There's other irrational numbers that have an even bigger irrationality measure. As a matter of fact, I think the irrationality measure of E is infinity. Um, but anyway, just thought I'd mention that. But anyway, so how do we solve this problem? Well, here, when I show in these, this is part A, we can just apply the recursive procedure. So step one just says R00, which we write in binary as 0.0, and I'm writing a subscript of 2 after each of these binary, you can think of these as binary decimals, just a binary representation of R sub n. So our 0 is 0, the way we define it, and that's 0.0 and base 2. And then what we do, the rule is for step 2, we replace every 0 after the decimal point with a 1, and every 1 with 1 0. So we replace the 0 with just a single 0 for our 0 after the decimal point. We replace it with a 1. That gives us 0.1 in base 2, which is 1/2. Remember the number after the decimal point are halves, not tenths, because we're working in binary. So we will have 1/2, which is 0.5. And then I still got a pretty bad cold, but I'm getting better. R sub 2, now we replace the 1 after the decimal point with 1 0. This doesn't give us anything new, it turns out, because when you add a 0 to a decimal representation or a binary representation after the decimal point, it doesn't change the number. So R2 is also equal to 1/2. R3, this is where things start getting interesting, I think. Now we we replace we just do the same replacement. So the first 1 gets replaced by 1 0, and then the 0 gets replaced by 1. And that turns out to equal 5/8, which is 0.625. So I think you can see it starting to converge on the value of the rabbit constant, which is about 0.7098. Still has a way to go. You might notice something else interesting here. If you look at the pattern of bits after the decimal point, they always start out the same as the previous one. This rule in step 2, which I defined in the problem statement, this is what's called an inflation rule. And this is a rule for generating what's called a quasi-lattice, because this is a quasi-periodic sequence, it turns out. And it turns out that there's another way you can define. You can say that R n plus 1 has the same starts with the same bits as R sub n, but then we add the bits of R sub n minus 1. That's probably an easier way to construct this thing. So, for instance, to go from R3 to R4, there's a couple ways we could do this. We could use the inflation rules I told you, or we could just start it off the same way as R3, 101 after the decimal point, and then R2 started 10 after the decimal point, add that. So you get 10110. And that turns out to be 11/16, which is about 0.6875. It's already pretty close to the rabbit constant. And I'm not going to go through each of these values, but I just did these. I actually used Mathematica to compute these. I'll show you my code in a minute. But if you go all the way to R10, you get this really long binary representation. It turns out to have 55, I think it has 55 binary bits after the 0. I think I forgot to put the 0 R10 at the beginning. But anyway, those are the 55 bits after the 0, and the decimal representation also turns out that the number of bits is always a Fibonacci number. And if he calculated the fraction corresponding to R sub 10, I put a red box around it. It's this pretty enormous fraction. Really big numerators and denominators, but if you calculate its decimal value, it's already corrected 20 decimal places. Pretty amazing. So you can actually calculate the rabbit constant to 20 decimal place precision. Even a little better than that, I think maybe 25 or 26 decimal places. just by calculating R sub 10. Pretty amazing. Like I said, the rabbit constant is better approximated than ordinary rational numbers by ordinary irrational numbers by rational numbers. And I think you can kind of see how that's working here. Um, anyway, so that completes part A, and here's the Mathematica code I wrote to do the calculations. I wrote a function called rabbit constant approximation n. That's just the nth, that'll calculate capital R sub n. And I use the definition. I say capital R sub 0 is 0. That's the top line. And then that's the thing I'm calling as 0. And then these are strings I'm working with. So I'm just applying the inflation rules. I'm replacing a 0 by 1 and a 1 by a 1, 0. And then finally, when I'm done, when we get the final string after n iterations, we convert it back to a binary number. And then we, write it as a fraction. So that's what this code is doing here. And here's the output. And these were the same fractions I showed earlier. And you can see that the numerators and denominators get very big very quickly. And at the bottom of this slide, I computed the decimal approximations. And already, I think R sub 9 is almost correct up to 20 digits. I think it's correct up to 18 digits. So the last two digits of R9 are 9-4, and then the last two digits of R10 are 6-4, but all the other digits are the same. So, these do converge very rapidly. And that's part A. And then for part B, I asked for the continued fraction of R sub 10. And that's easy to do with Mathematica because Mathematica has a built-in function called continued fraction. So I just used it. I said continued fraction of the rabbit constant approximation of 10. And since R sub n is rational for every n, and the continued fraction of every rational number is finite, we don't have to worry about this thing running forever. It'll give you an exact answer. And here's the exact continued fraction of R sub 10. And if you look at the way it starts, here you can see the powers of 2, the 2 to the power f sub n minus 1, it turns out. So, the first coefficient, like I said, is always 0, but then after that, the next 8 coefficients at least, these are the ones that are also the continued fraction coefficients of R. Um, so it starts out 1, 2, 2, 4, 8, 32, 256, and 8,192. And I think you guys, if you're familiar with powers of 2, then you should recognize these as all being powers of 2. As a matter of fact, they're the first one is 2 to the 0, and then 2 is 2 to the 1, which is 2 to the f sub 1. So 1 is 2 to the f sub 0, 2 is 2 to the f sub 1, 2 is also 2 to the f sub 2, 4 is 2 to the f sub 3, all the way up to 8,192, which is 2 to the f sub 7. F sub 7 is 13. So I think it's pretty remarkable that the rabbit constant has this particular continued fraction. I might have proved this once. I can't remember. Maybe around the same time that I was able to calculate the irrationality measure of the rabbit constant, I might have also proven this result. I don't remember. But it's been known for a while, so I wasn't the first to prove it, obviously. Even though I may have been the first person to compute the irrationality measure of the rabbit constant. I think I was because I didn't find it in the literature anywhere. And I'm pretty sure the editor of Matt Wolf from Math World, Ed Pegg Jr., I used to know him. He was one of my coworkers at Wolfram Research. And, I actually have a lot of contributions I made to his website. I think 107 contributions altogether. That was just one of them. And I think if somebody else had computed the irrationality measure before me, I'm pretty sure Ed Pegg would have known about it because he's very good at doing math research. So I'm pretty sure I was the first person to prove that. Anyway, so that completes my video for today on the rabbit constant. Thank you for watching. Long live math, and I'll see you guys next time. Bye.